Okay, it's going to be just about almost ridiculous how excited I am the next 2 or 3 weeks of the summer program because this is my favorite part of math, like ever. Trigonometry, and it's funny, I hated it in high school. I will self-admittedly say I was terrible. I didn't study. This is the only part of high school math that I did not make an A. Just because I didn't put in the effort. And now on the other side of it as a teacher, it is my favorite. It is so interesting, and so much about math comes from trigonometry. Now, your parents will know it by that title. This is what they probably didn't even take a pre-cal class. They took something called trig. And you know, what is this stuff all about? Well, you see the tri in there, so you know it has something to do with triangles. So, I mean, it is the study of triangles. And we're going to talk all about, you know, solving all different kinds of triangles and this and that. But what's funny is that we first have to look at sort of how these things originate from circles. And that's kind of interesting. So we'll talk a little bit about the study of triangles, but how they originate from circles. But we will do all kinds of solving, okay? We're going to be able to solve any kind of triangle. Even if it's not a right triangle, we'll be able to find sides and all that cool stuff. So before we can do that, though, we have to understand the circles they come from and how to measure a triangle, okay? Now, this is going to be weird because, okay, well, I want to talk about angles, but what we're going to do when we say understanding angle measures is we want to think about an angle as being on a coordinate plane, okay? And I don't just want to draw a random angle out in space and say, what's the angle? Okay, that's called use a protractor. We're talking about if you're on a coordinate plane and you have to measure an angle, how are you going to do that? And you actually have a choice. There's different modes and different ways to measure things. Now, one note that I want you to write that's really important is that you need to begin your angle measure at 0 degrees, which is going to be east, okay? So what this means is like, okay, you know this, hopefully, right? North, south, east, west. Looks like this, okay? And if you know a compass is north, and then west, and then south, and then east, okay, we're going to always start our angle measures in the east. So if I draw a random angle, this would be the beginning of it, which, as a side note, that's actually called the initial side of the angle. And then we're going to stop our measurement really wherever we want. So like if you want to stay in the first quadrant, or if I just said, hey, draw me an angle of 45 degrees, then hopefully it makes sense that would be your angle. You start it here, you stop halfway to 90, and that would be 45. So that's just an example. But you're going to be able to measure and draw any way that you want. So we're going to start with degrees. Let's let this box be degrees because that's what you've known your entire life. Degrees means, you know, you're eyeballing it. If you start at 0, like I said, that looks to be about 45. If you made it all the way to the north, then that would be 90 degrees. If you drew a straight angle all the way across, that would be this 90 plus this 90, so that would be 180. Okay, and if we kept going around the circle, then that angle would be, what's another plus 90? 270. And then if we made a complete revolution, which can happen if we start here and we draw an angle that goes all the way around, then we could call that 360 as well as 0. Now this is going to be important because at any point if somebody gives you a degree or an angle, you're going to need to know what quadrant you're in. So like if I say, hey, sketch 100 degrees, you should know that it's in the second quadrant because you're going just past 90. So like 100 degrees, you'd start here and you'd go to about there. That would probably be 100 degrees from there to there. So notice we are working counterclockwise. We're starting in the east, and so you might want to add that somewhere. We always kind of want to work counterclockwise, okay? Counterclockwise. Okay. So So this is how you know how to measure, and if you're wondering, well, why in the world are these two boxes over here? Okay, it's because this is the year where you get to learn a whole new mode of measurement, and it's called radians. You will do this in physics and in precal. Radians and degrees, they measure the same thing, people. Keep in mind, these are both measuring an angle. It's just like doing it in a different mode. So it's almost like a Fahrenheit versus Celsius. We work in Fahrenheit, the rest of the world does Celsius. This is kind of the same. Non-math people do degrees. Math people do radians, but we're still measuring an angle. Now, since we have to measure angles beginning in the east, this is still 0, but I'm not going to write the degree symbol on it because we're not doing degrees, we're doing something called radians. And what a radian is, this is actually really cool. Radians are measuring the angle on the inside, but it's almost a comparison of the circumference of the circle to the angle that's in the middle, like to the radius. So your teacher's going to give you an exact definition, but basically it's almost like using perimeter around the circle or circumference to label the angle that's in here. And I need to say that because I'm about to call this something that you may or may not like. If we start here and go all the way around, that would be like completing one full circle. Okay, now let's think about the circumference of a full circle. Now that is the equation 2 pi r. Well, if we assume that our radius is 1, like if we don't have any special length or whatever, then that would mean one full trip around the circle or around the coordinate plane would be 2 pi. So if you base it on that idea of the whole trip around is 2 pi, then you can figure out how far these other ones are. So in other words, if I wanted to go like 90 degrees, like normally from here to here is 90 degrees, right? Okay, but I don't want to measure in degrees. I need to think of it as I'm 1/4 of the way around the circle, so I'm 1/4 of the entire perimeter, or the entire circumference. So what is 1/4 of 2 pi? Well, if you divide that by 4, you get pi over 2. So instead of measuring this with a 90-degree angle, I'm going to call that pi over 2. Now if I start here and go all the way around to what is usually 180, now I'm halfway around my circle. So what's half of this? It's pi. And then if I am 3/4 of the way around, I'm multiplying the entire circumference by 3/4. And when you multiply that by 3/4, you're going to get 3 pi over 2. So I think in physics, they're going to not really explain this. They're just going to tell you, and I can't remember the exact number, but they're going to be like, hey, 1 radian is equal to 57.3 degrees, or they're going to say something like that, and they're going to give you a conversion, but you won't understand why. But if you think of radians as having to do with circumference compared to radius, think of radians as circumference over radius. And if you define it that way in your head, then these numbers will make sense, okay? All right, cool. So now what? Now, some people, since they don't like working in this mode, I have a third box over here because your brain sometimes just needs to wrap its head around how far this actually is. Like, we know a distance of 0 is 0, right? But if I say pi over 2, you might be like, well, crap, you know, how far is pi over 2? Or what number corresponds to pi over 2? So this box over here is still going to be radians, but this is going to be radian approximation as a decimal. Radian approximation, and I'll put decimal right here. So we're still going to do radians. I'm just going to approximate these numbers. So like pi is easy because we all have memorized for the last like 10 years that pi is 3.14. So this is 0. This is 3.14. Now if I make it all the way around my circle, that would be 2 pi, or 2 times 3.14, which is 6.28. So all I'm doing, folks, is turning these into decimal approximations. Now, from 0 to 3.14, that's the halfway mark, so it needs to be half of that, and I think that's 1.57 if I take half of that. Now, if I go between this one and this one, it's 3 pi over 2, which would be 4 point something. So I guess I need to add a 1.57 to that, which would be, I don't know. Hold on, 5, 7, 4.71, something like that. Okay, so this is an approximation of radians, but as a decimal. And the reason for that is because you may be asked, like, okay, sketch an angle that is 2.5 radians. And so if you're asked to do 2.5 radians, you need to know that 2.5 is going to lie somewhere in the second quadrant, and it's going to be somewhere probably right in between these, okay? And maybe a little bit closer to this one. But that's the kind of thing you're going to have to be able to do. 2.5 degrees would be like baby angle right here. So they're very, very different. Look for the degree symbol. If you don't see a degree symbol, it's going to be either this one or this one, and that's how you're going to be measuring. So let's actually practice this concept, okay? Negative degrees or negative radians. Okay. Now, all that this means is if someone gives you a negative, like if they say, I need you to go negative 110 degrees and sketch that. Okay. All that the negative does is it makes you go around the circle backwards. So if we're supposed to be measuring counterclockwise, backwards now means clockwise. So instead of going up like we were here, you would need to measure a distance of 110 degrees, but in this opposite direction. You still start in the east. We always start in the east, but now we'll go down 110. So that would be 90, negative 90. So maybe like right there. That would be negative 110. And that's all that that means, okay? So negative makes you go the other way. So same thing with radians. If I give you a negative radian, you're going to go clockwise. So maybe it's like, maybe I say negative pi over 7. Okay. You do not know where pi over 7 is. I do not know where pi over 7 is. So instead of thinking of it this way, it might be easier to go ahead and type that in the calculator, and let's get a decimal, okay? So I'm going to type in here 3.14 divided by 7, and that would be a 0.448. Okay, so where would 0.44 be? Well, let's look back up here. If this is 1.57, then 0.44 might be about right there. Okay, so that would be if it was a positive pi over 7, but since there's a negative, I need to go this distance in the opposite direction. So I'm going to go that distance, but I'm going to do so down in this quadrant. So this angle right here, everybody, the red one, this is my negative pi over 7. This one that's in blue right here, that would have been if it was a positive. Okay, so hopefully that makes sense. It's going to get better with practice, I promise, but that is how it works. Okay, coterminal is going to be a new vocab word for you. Coterminal is just fancy talk for multiple angles that have the same name. Let me word that a different way. How about coterminal? Let's do this. Coterminal angles. Think multiple revolutions. And all this means is earlier I was talking about, like, if you're on the coordinate plane, if you wanted to make a trip around the circle. You know how I called this one 0 or 360? Okay? If it's 0 or 360, well, that's if I go around the circle once. What if I kept traveling around the coordinate plane another time? So if I took another lap, then I've gone how many degrees? I've gone 360 plus another 360, and I've gone 720. That, my friends, is a quote coterminal angle. It's multiple angles that land in the same spot, okay? So angles that end up in the same spot. So it's pretty easy because the only way for an angle to end up in the same spot is if you add an entire revolution to it. So if you want a formula for finding coterminal angles and you're in degrees, you take the angle that you have and you either add or subtract 360 degrees. That's all there is to it. This is your formula, angle plus or minus 360 degrees. Now why can I say minus 360 degrees? Why do you think it's okay for me to put that minus there? Okay, if you didn't figure that out, it's because I can travel around the circle counterclockwise, but I could also travel around the circle clockwise. And if you're traveling clockwise, what does that mean? Right back up here, it means that the angle is negative. So that's why it's okay to subtract 360. So as one more example, okay, like if somebody said, okay, give me a coterminal angle with 35 degrees, okay, then I would just take 35 degrees and I would do this to it, 35 plus 360 and get an answer, 35 minus 360, and I'd get a different answer. So it would either be 395 or it would be negative 325. These two angles and this one are all in the same spot on the circle. They would all end up in the same spot on the coordinate plane, and that's what it means to be coterminal. So sorry if that's super redundant, but I will tell you this is the hardest part for pre-cal classes. I don't know why, but it kills people. So keep these notes, put a big star on them, okay? Now, coterminal angles in radians, same exact thing, except we're not measuring with degrees, we are measuring with radians. So I'm going to take this same formula that's right here and I'm going to make one adjustment. It's still the angle they give you, it's still plus or minus, but if I'm in radians, guys, I can't put 360 degrees because we're not in degrees. If you look back up here, what is the same thing as 360 degrees? Well, 360 degrees is one complete trip. One complete trip in radians is 2 pi. So I'm just going to replace, actually, I'm going to freak out a little because that won't move. There we go. I'm going to replace that 360. Dang it! Sorry, I'm challenged with technology sometimes. I'm going to replace that with a 2 pi. So it's going to be the same picture, the same idea, but I'm going to be doing add or subtract 2 pi instead. So as an example, if somebody said find coterminal angles for, let's go back to that pi over 7 thing we just did, pi over 7, okay? Well, you may not know where pi over 7 is exactly. You don't need a calculator for this. All we're going to do is take this angle that's given and we're going to add it to 2 pi and then we're going to subtract 2 pi from it. And this, you know, it's just fractions. Don't wig out. Put that over 1 and you need a common denominator because we're adding fractions. So if I need to make this one a 7. Now if I make this denominator a 7, this becomes a 14. So what is pi plus 14? Pi, well, it's 15 pi over 7. If I do the same thing down here, I make this a 7, that becomes a 14. Now I've got 1 pi minus 14, that's a negative 13 pi over 7. Okay, cool. So these will end up in the same spot as you travel around the coordinate plane. They will end up in the same spot as that pi over 7. Okay, well, it just means that one of them went an extra loop around this way, and one of them took one little loop backwards and ended up there that way. And that's coterminal angles. Okay, this is a long video and a lot of information. If you would like to stop and go do like half your homework, that might be smart because it's almost like I'm giving you, you know, a week's worth of stuff in one video. When you're ready and you've tried a few and you're ready for more info, come on back and we will do page 2 of this notes guide. Okay, so assuming that you took a break, or even if you didn't and you're just ready to go, we're going to now talk about conversions, okay? So this would be, if you don't want to memorize all those circles I showed you a second ago at the top of those other notes, and you just want to be able to take a radian and put it in degrees or vice versa, how can we do that? Okay, well, the conversion is really pretty easy. It's a multiplier, okay? It's just a multiplier. If you want to go from radians to degrees, then you take your radian that you have and you multiply by 180 over pi. Okay? Now, the reason that works is it has everything to do with setting up a proportion where you're comparing the circles that we drew above. And hopefully that makes sense, because if you look above, 180 degrees is the same thing as pi. And so it's like we're doing a proportion where we include these two things, and just by multiplying it by what we have, things will work out. And I'll show you an example. Degrees to radians, okay? So now other way, if you have a degree and you want to turn it into radians, it's the same bloody thing except you flip-flop this. So the way that I used to remember it or teach my classes, I would say, okay, think about what do you want. If you want degrees, degrees is on top. If you want to get to radians, then pi is on top because pi is a radian, okay? So as an example of each, let's do let's say that somebody gave me, well, we'll just do one that we know is going to work. Let's do pi over 2. Now, if you look above, pi over 2 is at the very top. It's at the north. So the answer to this should be 90 degrees. So if we take that and we do what I said, we multiply it by the 180 over pi. Then when you reduce those and you reduce that, you do in fact get 90 degrees. Okay? And now let's do a conversion from one of the other ones, degrees to radians. Let's take the one at the bottom that said 270 degrees. And if we want to turn that into a radian, like let's say you forgot what the radian was supposed to be, then you would just take 270 and multiply it by pi over 180. Notice I'm not getting a calculator, kids. I'm just reducing fractions. So same thing here, just reduce the fraction. It'll be 270 pi over 180, and then I'll reduce. Let me divide out of 10, divide out of 10, divide out of 10. Now what goes into 27 and 18? Doesn't 9 go into both? So if I divide by 9, it's 3 pi over 2, which is what we have on page 1 of our notes. So that would be the conversion, and that's all that has to be done. Now, to extend this to the whole, like, why are we doing this, you know, or what use will it be for me? Well, it involves SOHCAHTOA. So this is a throwback to geometry. And in geometry, you learned SOHCAHTOA, and that was to help you with all kinds of stuff, right? You learned that the sine of an angle, and I'm just going to call it I'm going to call the angle theta. I don't know if you've seen this symbol for theta before, but it's a Greek letter of the alphabet. A lot of people use it to describe an angle. The sine of theta equals the opposite over the hypotenuse. The cosine of an angle is equal to the adjacent over the hypotenuse. And then the tangent of an angle is the opposite over the adjacent. So those are things that you remember from geometry. I'm about to show you how we're going to use them with what we just now talked about, but before I do that, this says defining the 6 trig functions. I've only shown you 3, sine, cosine, and tangent. That's all you learned in geometry. Now that you're in precal, you're going to learn 3 more. The 3 others are cosecant, secant, and cotangent. Let me write that out in case cosecant, that's cosecant, secant, secant, and cotangent. So this is them actually like spelled out legitimately. These are the abbreviations for them. This is not some newfound weird mess of something. All that this is these are the reciprocals of the ones that you learned in geometry. So if sine is opposite over hypotenuse, then the cosecant is flipping that, and it would be the hypotenuse over the opposite. If cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. And then last, if we do the reciprocal here, it would be adjacent over opposite. So it's just the reciprocal, and I wrote them next to the ones that they are the reciprocal of. In fact, the name of these are called the reciprocal trig functions. All right, so these three are the reciprocal trig functions. These are just the normal, the whole world knows them. Okay, so what we're going to do with them is take the knowledge of measuring in radians, take the knowledge that you can draw a triangle on the coordinate plane, or even not on a coordinate plane, but we're just going to work on, like, you know, how you would solve a triangle or answer questions about those 6 trig functions, okay? So how would that look? This says defining a trig function given a triangle. So what that means is, like, let's pretend you are given this. Now, I will say this, I didn't put the word right, but it will be a right triangle every single time, okay? And if it's a right triangle, and let's say that you're given like 4 and 5, and then maybe they give you theta is here, okay? All of this junk will be given, okay? And if this is what's given, and they say find the tangent of theta, if they want you to find tangent of theta, what you're supposed to do is look at, okay, where is theta? And then I would label the sides of my triangle. So if this is theta, then this fella over here is the opposite. This is, of course, the hypotenuse because it's across from the 90-degree angle. And then this over here is the adjacent. Now, we don't have the adjacent, so sometimes you will have to solve for the adjacent on your own. And you would do that with the Pythagorean theorem, okay? So like if you don't know this and you're like, oh, I don't know what's in x, then it would be x squared plus 4 squared equals 5 squared. And you would just solve it with Pythagorean, and you should get 3. Now, you might have already known that this was a 3, 4, 5 triangle, and that's quite awesome if you remembered that from the past. But if you didn't, now you remember. And even if you didn't remember, you've got Pythagorean theorem. So once you find all the sides and you label them with opposite, adjacent, hypotenuse, now you're just answering the question of, like, what is the tangent? Well, tangent's opposite over adjacent, and so you would just answer it with 4 over 3. And, like, that's it. Y'all, that is it. It didn't say find the angle. It just said find the tangent. So 4/3 is your answer. If they had asked you about the secant of theta, if you look above, secant says hypotenuse over adjacent. Hypotenuse over adjacent. So that would be 5 over 3. And you would stop right there. So that's the beginnings of the application of the 6 trig functions. It's going to get way crazy intense later, but for now, it's good to just practice where things are located and how they fit together. Now, defining a trig function given another trig function. So sometimes it's going to say, okay, smarty pants, find the cotangent of theta if the sine of theta is 12/13. Okay, so if you're given this, then it becomes like, what? You just want to draw your own triangle. That's my recommendation, okay? Draw your own triangle. I don't even care what it looks like. I usually make mine look like this. I don't know why. It's a habit. But I always kind of have this chilling out in the left corner. So I draw a right triangle. Put your theta wherever you want. I'm going to go bottom corner just because. But you could put it anywhere you want as long as it's not the right angle, okay? Now, if the sine is 12/13, we got to think about what sine means. Sine is opposite over hypotenuse, okay? So make sure that the 12 goes opposite where you've labeled, and make sure that the 13 goes on the hypotenuse, and then it's your job to find the missing side. So once again, you either know this triangle from geometry, or if you don't, use the Pythagorean theorem. Okay, and solve for it. 13 squared equals 12 squared plus x squared. When you solve that, you should get a 5. And now that you know all the sides, now we find what it wants. So it wants the cotangent, and cotangent just means the opposite of tangent. So if tangent was TOA, O over A, this is A over O. So the adjacent over the opposite would be 5 over 12. And that's what it wants, okay? So you're going to have a lot of homework problems to practice this. I'm sorry this was a 30-minute video. It's probably the longest one all year. Well, there's one more that'll be just this long. But this is important stuff, and it's good stuff, and it's a good foundation for things to come. So good luck trying all your problems. I'll see you on the solution video.